Thank you very much for the introduction and to be part of this day. Really interesting presentations thus far. So hopefully I'll continue in that trend. Hopefully everybody can see a screen there. Again, as Joe said, my name is Ron Chapple. I'm the founder and CEO of G01. We are a survey mapping company specializing in electric corridors. We also do a little bit of oil gas corridors, coastal corridors, and some specialty wide area, but really at least 70% or more of our business specializes in the electric corridor area. So we'll talk a little bit about wildfire risk mitigation using data and what that can do for us in the future. But a little bit of a reference as I was researching, really what to say and why do we do this. I came across some interesting statistics. And first of all, I'm not a scientist. I'm not an engineer. My background actually came out of the commercial photography where we had to use data in a different way. And now I'm part of the team at G01 that says, what if? And we look at everything from a different perspective, trying to figure out, well, what if we did this? What if we did that? How could we make a difference? So distribution, a few years ago even, distribution was barely mentioned. It was barely surveyed. There wasn't much interest at all. But in the last few years, that has significantly changed. And this year, just since the beginning of March, that transformation of working at the office to working at the home has significantly ramped up. It was already underway, but from what I was reading, we ramped that up by about 5 years, increasing the importance of getting power to everyone's home. Certainly we have a lot of climate destabilization going on. Distribution poles could be, a young pole might be 30 years old, and old ones could be 50, 60, 70 years old. They're also wood, which can sustain a lot more environmental risk. And now we have the emergence of microgrids. All of these adding a lot of effort or a lot of interest to the distribution circuit. If we look at just a chart, this is from Sense Data on residential demand. The orange line was 2019. This is, I believe, at the end of March or April this year. The blue line is this year. We can see that dramatic increase in residential demand for electricity, particularly in the middle of the day, where before the middle of the day had a dip. Now there's almost an increase at the middle of the day, and the demand is happening, the high demand is happening earlier in the day. Climate destabilization, just a couple of weeks ago, I think we had the first event of simultaneous hurricanes in the Gulf. For several years now, we've had 12-month fire seasons. There's no more break. We have shorter winters. An interesting statistic or fact that I found is that with shorter winters, there's not enough time for cold to kill insects. And those insects infect the trees die, the trees fall down, and now we have a ton more fuel within that forest environment where there could be distribution lines. Also, talking a little bit about that 12-month fire season or kind of rolling risk. This is, the map on the left is now. This is September. We have a ton of risk, essentially almost the western part of the country, a little bit in central Texas. The green are where those, they had a ton of rain and the hurricanes have gone through. But just a month or so from now, that area turns to the high risk fire zone. And where do fires come from? Well, fortunately, only 10% of fires, according to the California Public Utilities Commission, are started with down power lines. It's not, in the scheme of things, not a significant source in terms of all ignition sources. However, just this year, from January to August, we've had almost 40,000 fires. That's when you start doing the math on 10% of 40,000, that's a lot. And what do we do? What does G01 do to help prevent and mitigate the risk of wildfire on distribution lines? If you're fortunately in an area that doesn't experience any wildfire risk or minimal wildfire risk, what we found is that the same 3 tiers also apply to any type of storm where you need data to detect and determine which poles might need to be put into a pole hardening program. We have first, conditional assessment, structural integrity. There's a lot of phrases for that. It's really getting a high resolution image for a person to look at, to analyze what is the hardware state, what is the condition of that hardware. Number 2, a lot of people today have touched on that, is vegetation encroachment. How close is that vegetation to the wire? Is it a grow-in risk or is it a fall-in risk? And then clash detection, detecting the distance between 2 conductors to prevent arcing. It's always been done for 10, 15 years now under a NERC program for transmission, and now it's happening within the distribution field. The first step is absolutely to get the highest resolution LiDAR that you possibly can. We know our clients want, higher resolution, they want it more frequently, and they want more of it. It's critical because, first of all, it gives us really good data on conductors and poles to do quick automated analysis, and it allows us to accurately geo-position poles and structures and connection points. How do we do that? About 4 years ago, G01 essentially invented one of the first dual sensors. Our goal was to take that rich data that is acquired in a mobile system and put it on a helicopter. Essentially, it's our airborne mobile data collector. We have a scanner that is canted up and one that's canted back. And then we have 350 megapixel cameras underneath, one looking nadir, one back, and one forward. What those scanners do is the one that's facing up, as the aircraft approaches the pole, we're scanning the front of the pole. And then as we go past, it's picking up the back side of that pole. So we're picking up a ton of data here. And on a lattice work, on a big transmission, you might be able to get by with just a single scanner because of the angle of the pole and the angle of the lattice work. Distribution poles are typically wood, they're small, and of course it rained the night before, so you need to push as many points as possible down onto the hardware. And then, as I mentioned, that LiDAR data allows us to accurately do a geo-correction of the points. Probably not a problem that's uncommon to many utilities. The data collected of distribution could have been collected 10 years ago, 15 years ago, and perhaps the devices weren't as accurate or the methodology wasn't as robust at that time. This is an example of the red dots are the information provided by the utility of where the poles are located or where they believe the poles were located according to their GIS database. The blue strip here is the LiDAR path, and the black and white dots are where the actual poles are located. We recently did a project, found the average error was in the 200 to 400 foot range, with some data sets as much as 5,000 feet off. So the first thing that we do, as I mentioned in that structural integrity, is to create images. The reason we're doing images from the air is that most of the structural damage or structural integrity issues start at the top of the pole. This came about, there was a fire that was started 2 or 3 years ago. The pole that started was the source of that ignition had been inspected by boots on the ground just 2 days earlier. And they did their job perfectly. They were looking up, they saw no issues with the pole, there were no let's say negative marks given for that pole. But 2 days later, that pole fell and created a fire. Fortunately, just a couple hundred acres put out quickly. But that turned some heads in saying, you know what, we've got to get above the pole to see what is up there. So the image on the left represents that full width of the image. And then if we look at this red box, we can get in, and of course we can see this big crack already forming in the full picture. But when we zoom in at a one-to-one view, we can see there's already another crack forming, and then just a lot of stress being put on these cross arms. A few samples of the work that we do. We're also kind of old school, new school. We're using photographers in a helicopter. We're flying at anywhere from 400 to 600 feet and as far as 700 feet offset from the pole. We're picking up an average of 500 poles a day, depending on the area. Sometimes it's only 300 or 400. Sometimes we've had 800 poles per day acquired. We're working with 2 photographers. One is photographing one side of the pole and the other is photographing the other side so that we have a comprehensive view. And this is the full width. And if we zoom in, this is the level of detail that we're seeing. Again, remember, this is from 600 feet away. Another sample. In this case, you know, our eye is drawn to the hardware, looks in really good condition, but really what we want to see is this cross arm that has sustained significant woodpecker rot damage along here, and once this crack continues, this insulator is gone. Our field crews and pilots are also trained to identify threats from the field for immediate response. You know, we're looking for blown, you know, insulator boots that are blown off, certainly looking for any significant woodpecker or structural damage, and then looking for environmental where there has been a bird nest. Where is this going? Right now, we currently take the data, acquire the data, and then download afterwards, and then process it. Where we're going with that is real time. We want to take these incredible high-resolution images, and while we are in the aircraft, start that onboard downloading and processing of the data. We're going to be running it through IBM's Visual Insights and their AI, and kick out just the structures that don't meet spec or have issues. That data can be sent either via satellite link or a bonded cellular 5G to a common data environment where any number of people can view it from really anywhere. It could kick out a work order. It can go to engineering. It could go to an incident command. It could send a photo with the area highlighted. The quicker we can get data, the more lives we can save with that information. A little bit about our relationship with IBM. We are an embedded solutions partner for their Visual Insights product. That Visual Insights allows the training of data with a very small sample set and for a number of uses. The uses you see here are, first, just simply to find the pole within the image, and to then take this, crop that in, and find the cross arms, and find the insulators, and make an inventory count of those. From that point forward, the insulators can be zoomed in on, and potential, if we have the training set data, potential flashover, damage, cracks detected, and certainly cracks like this in the cross arms detected. Another example that we've been using the Visual Insights for is training it to look for bird nests. Even the sharpest photographer's eyes, when you're photographing 500 plus poles a day, might miss a bird nest or it might be in the shadows. Well, the AI doesn't really care. This is the training set that we gave it. We fed the AI engine, the machine learning software, only 10 samples of different bird nests, and it was able to go in and start finding bird nests right away. The same on pole tags. We kind of live for pole tags to help us inform where the correct geolocations are so that we can match that up accurately with the client data. So in these two samples, we're detecting which poles will have a pole tag. The second tier is vegetation encroachment, which is a familiar subject. The first part is that it has to be automated. There is just too much data, too many circuits out there, too many trees to not do it in an automated basis, and to do it as a 3D visualization so that you can look at this from any perspective, see the distance, know if it's growing or falling. And then that data also needs to be streamlined for field use. Whether it's an iPad or a custom, rugged laptop, we need to take that intense data set that could be 100 to 200 points of LiDAR data. When we run it through PLS CAD, of course, we're going to build a very simplified model. And, the power of PLS CAD is going to help us identify every point that is in violation. But this is even too much information to send into the field. So what our team has done is to write a script that decimates that LiDAR data to 1 point every 10 feet. And it puts that into a KML for field use. It also creates different colors for the different levels of threat. So for example, the blue might be a 20-foot three-dimensional distance, where the orange might be a 10-foot. It also outputs that CSV deliverable that can go to the client to be ingested into their analytics. And the third tier is clash detection. We take a very complex forest environment. We build, using PLS CAD, build the model to create the conductors and create the wires, and then go in and start analyzing the place within the span where the connectors are closest together. So we're determining what the closest distance is between any two conductors. We're also determining the height of attachment. So we have an XYZ for every attach point and the distances between any of these connectors. And from there, the data, if it's just on a single desktop, doesn't work. It's kind of data that's captive. So that data needs to get out to a common platform. In this case, the data is uploaded, automatically processed, online analytics done, and contextual information is being created. We look at this screen as an overview. We have a contextual map of where it's located. We know that there is an image of this particular pole. All of the wires have been classified. The orange is the network. We see the lean calculation automatically. We see the distance and lengths of the span. And then, interestingly, we can just do a right click and open up a Google Street View of where this is located. Take that a little bit further. We're looking again at pole lean. It's taking that coordinate at the base of the pole, throwing up a line at 90 degrees, and then measuring that offset and doing an automated calculation of the pole lean. In this case, 5.92 degrees. we say, well, is that right or not? Let's just get our eyes on it and open up Street View at that point and say, yeah, that looks like a, a 6-degree lean at least. It has a lot of heavy underbuild on it. And we do know that there are guy wires. We can take these 2 points of the base of the pole and the where the guy anchor intersects the ground and start to calculate a lead ratio as well. So very rich information. It makes this LiDAR data and these analytics, by putting it into a common data platform, accessible to everybody. Another aspect that we can do, taking this exact same data set, taking another line of data in knowing the height of this pole, we can calculate a bury depth. In this case, as everyone probably knows, poles are 40 feet, 45 feet, 50 feet. The industry standard is to bury a pole 10% of its original length plus 2 feet. We run the analytics on that, and we find that this pole that is already leaning is also underburied by about 8 inches. Definitely a candidate to, for someone to go take a look at. And long term, what do we do with this data and where do we go from here? We need to recognize that new trends are affecting distribution. The climate destabilization, increased residential use, longer winters, a 12-month fire season. A spark is a spark. It doesn't matter if it comes from I think it was just a fire, unfortunately, in California, where there was a chain dragging off the back of a truck. It kicked up a spark. A distribution circuit can kick up a spark just as easily as a transmission circuit can, and distribution is a lot lower to the ground. There's a lot more vegetation typically around distribution. Distribution is not cleared to the same corridor width. Most utilities clear maybe 6 to 10 feet either side of a distribution line, where in the transmission world, it might be 50 to 75 to 100 feet of clearance. We need to acquire data first of those critical circuits. Undertaking a distribution analytics, wildfire risk mitigation project is new to many utilities. It's a huge project. It's an investment that may not have been planned. So we suggest that companies start doing a proof of concept. They start acquiring data of critical circuits. And as they acquire that data, the next step is to create a comprehensive analysis that can be used as a baseline to then create a feedback loop to say, okay, we found out this information. Now we can field check it and bring that information back to see if we need to make any changes. I truly believe that any data collection, any analytics needs to be organic. It needs to be informed by the previous data set, the previous analytics that were discovered, and by everyone that's a stakeholder so that the data has the most use. We need to get out of what we can call verticals within a company where by having this common data platform, the vegetation team, the engineering team, the maintenance team can all share that same data to reduce the cost overall of that collection. And then really brings me to the last point, is that data has to be archived in a common viewing platform. It has to be accessible easily online to anyone at any time. So whether that's let's just say a severe incident of an earthquake or a road or bridge closure where people can't get to work or can't get to where they need to be, being able to view that data, as we've learned now, working at home from COVID, is that access to that information online is absolutely critical. So, and Joe, thanks very much. I'm probably maybe a little bit too quick there at half hour or so, but here's my contact information if anyone would like to continue the discussion.
Thank you, Ron. Very interesting talk. lots of ideas there for people who manage these kinds of systems or who collect data. I know that fires started by power lines are top of mind for a lot of people, especially with the PG&E experience that we're probably all aware of. Um, so, so certainly, I learned a lot about some of the benefits and downsides of doing this kind of data collection with different kinds of technologies. Obviously, you think that this is one of the best ways to do it. So here's a question regarding that from Lorenzo. Are there cases when a UAV with LiDAR can be utilized, and when is that justified? You're muted right now, Ron.
Sorry about that. Lorenzo, great question. I believe that there has to be multiple platforms available and multiple ways to access the data. So whether that is, airplane, helicopter, UAS, people walking, mobile, you need to have access to all of those tools and then choose the best tool for, not for the overall project, but that part of the project. So for example, if there are distribution lines really close to an airport and for whatever reason it's difficult to get permission to fly a drone in that airspace, then a helicopter might be more appropriate. On the other hand, helicopters, even though we're moving at 20, 30 miles an hour, if there's a noise concern, then perhaps flying a quiet drone might be the better option. So I always advocate for the right tool for that part of the acquisition.
I'm assuming that you have gone through quite a bit of trial and error to figure out your ideal configurations. For example, for that pod that you had attached to the front of the helicopter with two LiDAR units, one canted up, one canted down. And I'm assuming the one canted up is picking up the near side of the pole as you approach it. The one canted down is picking the far side of the pole after you passed it. So if you're using a UAV, while I've seen UAVs that which would have the payload capacity, most UAVs wouldn't be able to haul that plus three pretty heavy digital cameras and who knows what else you have inside that pod. But I'm assuming those are some of the caveats. If you have to use UAV, it may have to mean several passes with cameras or LiDAR set up in different configurations to pick up all the sites that you need to pick up.
And no, absolutely right, Joe. And there's, again, it gets back to what are the project specs? If there are 10 miles of distribution in a remote area, sending a drone crew might be far more efficient than sending a helicopter crew because of the mob time and the ferry cost. However, once you get anywhere over, 100 miles, then the helicopter becomes significantly more cost effective and effective in terms of production rate. So the numbers really change because the projects can be so different, but in general, on a larger scale project, using our system in the helicopter is collecting about 10 times more data per day than a UAS, but we have to get on site. So now you're balancing off the ferry cost with the productivity. So most projects are best when you take that kind of comprehensive approach and you're using, every platform that's available to you.
Thank you. So there was a comment you made, but you didn't explain yourself. So I'm going
to... You're going to put me on the spot?
I'm going to go back because I'm sure you know exactly what you're talking about and explain to the rest of us neophytes when you were talking about picking up LiDAR shots on the poles, and you said, of course, it's rained the day before.
What that means is, LiDAR doesn't do well with water. So, for example, if we're scanning a lake or a pond, it's just light, so it's going to come down and bounce off in a different direction. So, if the subject matter is wet, it's essentially a mirror surface, and the return is going to bounce off in an odd direction rather than back at the receiver within the sensor. And of course, rain makes the subject darker. So now you have low reflectivity, and it's the water has created a little bit of a mirror surface to it.
Okay, good. Thank you for explaining or helping us remember some of the basic laws of physics.
I'm not a physicist, we'll put it that way for sure.
Well, you certainly have the physics at hand for this kind of thing.
Thank you.
So I have another question regarding that pod or whatever you might call it that you attach to the front of your helicopter. You mentioned that you're flying about 20 or 30 miles an hour. So what kind of frame rates or burst rates are these cameras? You mentioned you have 3 cameras. Are these pictures being taken, or are you only manually triggering them?
Okay, John, probably explain just a little bit more. The 20 to 30 miles an hour is when we're acquiring the handheld high resolution images of each pole with the 800 millimeter lenses. When we're doing the LiDAR collect, we are typically flying anywhere from 40 to 60 miles an hour. And if we're doing the high resolution, the 150 megapixel with the phase 1 cameras, we typically will either time trigger or will proximity trigger. But because the data that we have on where the line actually is may be different than where the line actually is, we'll typically time trigger at a 1 to 2 second rate. So 1 picture every 1 second, 1 picture every 2 seconds or so.
Okay, good, thank you. So going back to your photographers, where you have 2 photographers manually taking pictures, you talked about using the photographer to get 2 sides. I assume, because I was confused at first, because I had to get my head into that space in the helicopter, I'm assuming one photographer is looking ahead and one photographer is looking back. Is that right?
Yes, that's correct. So, and we do that for efficiency. It's much more efficient to put a second photographer in the helicopter than fly a route twice. So we're offset, from the line and flying down the line. The other thing I should mention, Joe, is that we have our own custom devices that have a combination of sensors to actually determine the ground intercept of the picture when it's being taken. So we're feeding in IMU GPS data just like we would on a survey camera, but we're feeding it into a handheld DLSR. So in real time, we are calculating the center of every image and that intercept on the ground. So that when we land, when that data is downloaded, most systems will tell you where the picture was taken from, not where the picture is taken of. So that helps us out greatly. And then we have a system, again, that we've written a lot of scripts for geolocating and geoclustering data, and then attaching that data to the pole with vector scripts, so that when you have we just did a project we had in a little less than 2 months. We took 1.5 million pictures. So you can imagine there's a lot of data that has to be, sorted effectively.
So you actually answered the next question I was going to toss at you. that's an interesting proposition, because what you're telling me is that you are determining the attitude and the azimuth of each camera's central ray, if you will, and you are able to, I'm not sure what information you're using to determine where the ground is, but you can now determine where it intersects the ground, so you can get some kind of a georeference in the vicinity of the pole, and you have enough information showing the pole as well as the ground to be able to then back calculate to the fitting on the pole.
Yeah, that's correct. And it starts with that, really accurate LiDAR data. We also use, there were questions there earlier about ground control. We're typically using Trimble's PPRTX for our trajectory correction. Trimble specs are 10 centimeter XY and 20 centimeter Z. Our experience is that it's way better than that. It's more like in the 4 to 6 centimeter range in X, Y, and Z. So getting that data allows us first to find the accurate location of each pole, and then we take that corrected data and now line it up with the image position. So both automation and online viewing and moving all of that to real time are where we need to go. There's simply too many poles out there. I think there's what 400,000 or 500,000 miles of distribution, and there's 10 to 20 times that distribution. I don't know if anyone actually knows.
So if you can talk a little bit about the IBM system, and I didn't take notes on the name of it, even though I've encountered it before. Is that an out-of-the-box solution, or does IBM have to modify it to your purposes, or do you bring the customization for the application into the system?
So the latter, the last answer about bringing the customizations to it, it would be most appropriate. What's really cool about the IBM system is that what makes machine learning difficult is having enough good training data to be able to train the system what to look for. So in the bird nest sample and in the cross-arm sample, we started with maybe 15, but certainly less than 20 samples. You can go in and do this all online, so the customer can do it themselves or a technician can do it. So we take that very small subset of training data, and then we use their own algorithms to essentially mess up that data. So we'll flip the data upside down, turn it from side to side, make it fuzzy, crop it darker, lighter. So now that training set that may have started with only 15 images now has been translated into several hundred images. And it trains on those several hundred images really in a matter of hours. And then you can start running data through it.
Yeah, that's fascinating, because I'm not sure I'm aware of many other people in the geospatial industry using it. Tell me again what the name of that system is that IBM.
Sure, it's called Visual Insights.
Oh, yeah.
And it came out of I believe it came out of their Watson program from a few years ago, and
Sure.
they've renamed it Visual Insights. Another advantage is that a number of utilities already use an IBM backend, database, and those merge together really nicely.
Very good. So when it comes to your desire to support the ability of your clients to access the data you're collecting in real time, do you really think that you can transmit that much data in real time? It seems like a lot.
Well, what the workflow that we have concepted, Joe, is the client, the maintenance team, the veg team, at that moment, they don't need to see polls if they're not an issue. So now if every poll has an issue, perhaps that could, be pretty data intensive, but typically it's not going to be every pole. So you're quickly analyzing the pole. You don't have to send that high resolution image. They just need to know that there's an issue with that pole. So a picture of the pole with a little bit of maybe a circle around the issue, and the coordinates are all they need to get started.
I see.
Just enough information to get by. We're living for that, that fast satellite data, from either the SpaceX, Boeing, whatever star system that's going to blanket the world, or 5G everywhere. And the other part too is that unlike an airplane, we're typically flying at 400, 600 feet, and if you look at your phone, you almost always have 4 or 5 bars of LTE. So we're in a good environment for being able to use 5G in the future.
I see. So basically, what you're saying is part of the solution here is to do decimation, but in a different way, in terms of what you send to your clients.
If manufacturing is just in time, this is just the right data, something like that. I need to come up with a good tagline.
Yeah. There's money in that. And then the final thing I had in my notes here is when you're looking at vegetation, have you done any studies about your ability to detect changes in vegetation? In other words, temporal observation. So you fly the same line over and over again, and to be able to zero in where there's actionable places where there's action required, because the system can immediately find those new encroachments or potential encroachments.
It's a tough situation to do change detection on vegetation. Simply with trees blowing in the wind, a tree under leaf or not under as much leaf can, every one of those are creating a change. And I think we're still waiting on some advancements there to really use change detection for vegetation analysis. Certainly on hard objects, it works really well. But I think we're not quite there yet, or at least in the software that we've viewed or tried to put together. But that change detection, it's, I like to think of that data as the first collect is really just a moment in time. The second time you collect that data, you have a comparison between A and B. The third time you do it, now you can predict trends. And that's the real value, and why we're having our clients ask for more data more often.
Thank you. Well, we've used up our time together, so it's time to move on. Ron, thank you again for the interesting talk and helping us get back to basics in physics. It's always interesting how much knowledge of really fairly elementary science can help understand why sometimes we have mission failures. It doesn't have to be as sophisticated as not calculating the correct conversion from kilometers to miles, as happened in a recent flight to some planet, I forget which one. But they happen here on Earth all the time, and it's really interesting to get those insights, because I think your feet on the ground, even though your feet are not on the ground, knowledge, your understanding of some of these phenomena, I think will speak volumes in the minds of the people who are attending this conference, because it's that kind of thinking and that kind of observation of our physical world that helps us generate more quality data. So thank you. And
thank you, Joe, and thank you everybody for listening. I appreciate it.